I hope you are doing well, and I think we have several parts from the previous week. So let's start. I will share the lecture notes for the first week. Okay. Can you see my desktop now? Okay. So we continue with the solution of the ODEs. As I told you, we deal with a second order of ODEs, and we discussed the homogeneous solution for this type of equations. As I told you, you need to first form these characteristic equations. Here you can see the characteristic equations for a second order ODE is equal to the coefficient of the second derivative times by alpha squared, the coefficient of first derivative times by alpha, and the coefficient of the y, or the unknown function. It must be equal to 0 because we want to obtain the homogeneous solution. Next, we need to obtain the roots of this equation. We will have three options. The first option, the roots are real and distinct. So alpha 1 and alpha 2 are two roots for the characteristic equation. So the homogeneous solution is C1 exponential alpha 1t and C2 exponential alpha 2t. The second case is when we have two complex conjugate roots. In this case, the homogeneous solution is equal to the exponential of rho t, which rho is the real part of the roots, multiplied by C1 cosine theta t plus C2 sine theta t, and theta is the imaginary part of your roots. And finally, the last case, which is the double roots, we have a double roots of alpha in your characteristic equation. So the homogeneous solution is equal to the exponential alpha t multiplied by C1 plus C2 times by t. So this is three different types of the homogeneous solutions. The next step, we need to obtain the particular response. Okay, so for the particular solution, in this course, we will focus on the method of undetermined coefficients. The first case, we can assume that the ft, or the non-homogeneous term, is equal to a polynomial of order n. So we can conclude that the particular solution is equal to this term. As you can see, the particular solution is equal to a polynomial of order n, similar to the non-homogeneous terms. We have n unknown coefficients, d1, d0, d1, d2 to dn. So we have n plus 1 unknown coefficients, and these coefficients will be obtained by substituting into the main equations. The second case, assume that we have a non-homogeneous term in exponential form. For example, it is b1 exponential beta t, which b1 and beta are known for us. This is the given data in your equation. So the particular solution is considered as d naught times by exponential beta t, which beta is the same beta in your non-homogeneous term, but d naught is the coefficient of your particular solution. And to obtain d naught, again, we need to plug in into the main equation and solve for d naught. And finally, the last case, which is important in this course, is the cosine or sine function. assume that, for example, ft is equal to b1 cosine beta t. In this case, b1 and beta is again known. We know how much is that. There are some given data in your problem. The particular solution will be considered a combination of cosine and sine with coefficients d0 and d1. It is equal to d0 times by cosine beta t, which beta is the frequency here in your non-homogeneous term, plus d1 times by sine beta t. As you can see, the particular solution includes cosine and sine, both cosine and sine functions. Despite here in the non-homogeneous term, we only have cosine functions. Again, if the non-homogeneous term was equal to, for example, b1 times by sine beta t, again, the particular solution is the same as for the cosine function. Again, we will consider the same particular response. And to obtain d0 and d1, we need to plug into the main equation again and solve this equation to obtain d0 and d1. Okay, and as I told you, these coefficients d0, d1 to dn are constant coefficients, unknown constant coefficients, and they will be determined by plugging in the equations. Okay, so this is the procedure to obtain the particular response, and we can obtain the homogeneous and particular response separately, and finally the total solution for the equation is equal to the particular solution plus the homogeneous solution. Once you obtain the total solution, then you can use the initial condition or boundary condition to obtain the constant coefficient in your homogeneous response. So we can solve some examples to clarify more about this procedure. Do you have any questions so far? Any questions so far? Okay. Here is an important question. You can go through to this question, and if you can find the response, you can later send me your response, or in the next session we can discuss about the response for these questions. Why the particular solution is called a steady state solution and homogeneous solution is called transient solution? In this course, in vibrations, we call the particular solution the YP, which I explained in previous slide, is called a steady state solution, and the homogeneous solution, which is explained in the previous session, is called transient solutions. You can search regarding to the answer of these questions, and next session we can discuss more about why we call them a steady state and transient solution. Okay, here we have a system of several springs. We want to determine the equivalent spring constants of the system. We have 1, 2, 3, 4, 5, 6, and 7 springs. The stiffness for these two springs are equal to K1. The stiffness for this one is K2. These two are equal to K3, K4, and finally another spring with the stiffness K5. For this system, first we can find an equivalent for these two springs, which is equal to, these are parallel, so the equivalent the stiffness is equal to K1 plus K1, or it's equal to 2K1. We have another equivalent here, which is K3 plus K3, and it's equal to 2 times by K3. And then we will have a combination of 3 springs which are series, this spring equivalent 1, a spring with a stiffness K2, and a spring with equivalent 2, which is 2 times by K3. And finally, we can obtain the equivalent stiffness for this part. And this part is again parallel to K4, and it's equal to K4 plus, if we call it, for example, K equivalent, for example, 1, it's equal to K equivalent 1 plus K4. And finally, the equivalent of this system is series with K5, and we can find the total equivalent for this system. So let's show you on the slides. Okay, as I told you, here we have 2K1. Here you can see we have K2 and 2K3, which they are series. So the equivalent 1 for this system and for this part of your total system is equal to 1 over K equivalent 1 is equal to this term. And the equivalent for this part, which includes K4, is equal to K equivalent 1 plus K equivalent 4. And finally, the total equivalent stiffness is equal to 1 over K equivalent 2, which is obtained from previous part, plus 1 over K5. So this is a total equivalent stiffness for this system. Is it clear? Okay. Okay, here we have one differential equations from order 2 with non-homogeneous term. As you can see, the non-homogeneous term includes an exponential part and also a cosine function. So here we have boundary conditions. The boundary conditions is y at x is equal to 0 is 0, and y prime at x is equal to 0 is equal to 5. So we need these boundary conditions to obtain the constant coefficients in homogeneous solution. So as you can see, this is a non-homogeneous equation. So it has two homogeneous and non-homogeneous responses. And the total solution is equal to the homogeneous plus non-homogeneous or particular solution. For the particular solution, we have an exponential function. So it includes an exponential function plus another part, which is a harmonic, a combination harmonic of cosine and sine functions with frequency 5. And for the exponential part, we have in the power of the exponential term, we have 2 times by x. So first, let's find the homogeneous response for this equation. As I told you, we will have a homogeneous part and particular response. So we need to form the characteristic equation. As you can see, this is the characteristic equation. As I told you, here the coefficient of y second or the second derivative is 1. So the coefficient of alpha squared is 1. The coefficient of y prime or the first derivative is 3. So the coefficient of alpha is 3. And finally, plus the coefficient of y, which is 2, and it's equal to 0. So here we have an algebraic equation from order 2. Easily, you can solve this equation and obtain the roots for this equation using the delta method. We have the particular solution. As I told you, particular solution includes two parts. The first part is exponential part. Here you can see d naught times by exponential 2x, because here we have 30 times by exponential 2x. The second part is the cosine and sine harmonics. Here we have 10 times by cosine 5x. So the particular solution includes d1 times by cosine 5x plus d2 times by sine 5x. So we will have two harmonics combination of cosine and sine function. To find the homogeneous response, we need to obtain the roots for the characteristic equations. If you solve these equations, the roots are equal to -1 and -2. And we can calculate that the homogeneous response is equal to C1 times by exponential alpha 1 x, which alpha 1 is -1. So it will be C1 exponential minus x plus C2 times by exponential alpha 2 times by x, which alpha 2 is -2. So this is the homogeneous solution for this equation. To obtain the particular solution, we need to substitute into the main equation. You can see we have three unknowns, d0, d1, and d2. You need to substitute into the main equations and simplify and solve these equations to obtain d0, d1, and d2. If you substitute this particular solution into the main equation, which is equal to the second derivative of y with respect to x, so we need to obtain the second derivative of the particular response with respect to x. As you can see, the second derivative for this equation with respect to x for the first exponential term is equal to 4 times by d naught times by exponential to x. The second derivative for the cosine function is equal to -25 times by d1 times by cosine 5x. And the second derivative for the sine function is equal to -25 times by d2 times by sine 5x. And then we have plus 3 times by first derivative, as you can see here into the main equations. This is the main equation. We will have y second plus 3y prime plus 2 times by y. So we need to substitute here y p second as I told you, it's equal to the yp second is equal to 4 times by d naught times by exponential 2x. I don't know why the font here is, it has another extra line. I don't know why. So this is the y second for exponential term. For the cosine, it will be equal to -25 times by d1 cosine 5x. And for the sine part, it's equal to -25 times by d2 times by sine 5x. So we can plug in this y second into this equation here. The y prime, again, we need to obtain the y p prime, or the first derivative of this equation, into the first derivative of this equation with respect to x, and substitute here for y prime, and it's equal to 2 times by d naught exponential 2x plus -5 times by d1 sine 5x. You know the cosine 5x, its derivative with respect to x is equal to -5 times by sine 5x, and the derivative of sine 5x is equal to 5 times by cosine 5x. We can substitute here, and finally for y, we can substitute the same yp here and simplify. In the right hand side of equation, we have 30 times by exponential 2x plus 10 times by cosine 5x. So in the left hand side, the coefficient of sine times by 5x must be equal to 0. The coefficient of cosine times by 5x must be equal to 10. And the coefficient of exponential 2x must be equal to 30. So if you substitute and simplify, you can see the coefficient of cosine times by 5x is equal to this term. The coefficient of exponential 2x is equal to this term, and the coefficient of sine 5x is equal to this term. Now we can solve these three equations for three unknowns d0, d1, and d2. We have three equations. Here you can see 1, 2, and 3 equations. From the second equation, you can easily obtain that d0 is equal to 30 divided by 12. So this is d0. Then you can substitute into, of course, we don't have d0 in the first and third equation. So the first equation and third equations are a system of coupled equations. So you can solve d1 and d2 and obtain d1 and d2 from these two equations. For example, from the third equations here, you can obtain that d1 is equal to minus 23 divided by 15 times by d2, and then substitute into the first equation and obtain d1 and d2 for these equations. So in the next step, we have yp, we have yh. So the total solution is equal to the summation of yh plus yp. Here, this is the homogeneous solution, and this is the particular solutions. The particular solution is completely obtained. I mean, we have all of the coefficients d0, d1, d2, but we need to obtain c1 and c2 by using the initial or boundary conditions. So the next step, we need to use the boundary conditions. Here, this is the total solution. As I told you, the boundary conditions at x is equal to 0 is 0, and the first derivative with respect to x at x is equal to 0 is equal to 5. So at y at x is equal to 0, it means that here in this total solution, we should substitute, instead of x, we should substitute 0. So we will have c1 exponential 0 plus c2 exponential 0. Here, when you substitute instead of x, you substitute 0. Here we will have 0. This is minus 2 times by 0, which is 0. 2 times by 0, which is 0. Cosine of 5 times by x, which is 0. And 5 sine of 5 times by x, which is again 0. Here we will have c1 exponential 0 plus c2 exponential 0, 2, and finally we have cosine and sine of 0. This term is equal to 0 because the sine of 0 is 0. The cosine of 0 is equal to 1. And now we can simplify. So we will have c1, and you know that exponential of 0 is equal to 1 as well. So we will have c1 plus c2 plus 2.5 minus 0.3 is equal to 0. If you simplify this, we will have c1 plus c2 is equal to minus 2.2. The second boundary condition is here, this term. We need to obtain the first derivative of y with respect to x. Here we will have c1 times by exponential minus x. The derivative of this term with respect to x is equal to minus times by c1 exponential minus x. The derivative of this term with respect to x is equal to minus 2 times by c2 exponential minus 2x. The derivative of this term is equal to 2 times by 2.5 times by exponential 2x, which is 5 times by exponential 2x. Here, the derivative of cosine function is equal to minus sine. So here, the derivative of this term with respect to x is equal to minus 0.3 times by minus 5 times by sine 5x. And the derivative of this term is equal to 0.198 times by 5 times by cosine 5x. And finally, in this term, in this equation, which is the derivative of y with respect to x, we should substitute x is equal to 0. And again, we can obtain these equations. Here, again, we have sine 0, which is 0. We have cosine 0, which is equal to 1. We have exponential of 0, which is all of these terms are equal to 1. So we will have minus c1 minus 2 times by c2 plus 5 plus 0.99 is equal to 5. And if you simplify this term, you can extract the second equation, C1 plus 2C2 is equal to 0.99. By solving these two equations, we have two equations here, 1 and 2. You can obtain that C1 is equal to minus 5.39 and C2 is equal to 3.19. So we have two constant coefficients for the homogeneous solution, and if you substitute C1 and C2, finally you can obtain the total solutions with all of the coefficients. This is the total solutions. And now if you substitute, for example, at x is equal to 1, you can obtain that y is equal to minus 5.39 exponential minus 1. Here you can substitute x is equal to 1, and you can obtain the y at each x, at each corresponding x. Okay, any question from this example? Is it clear? Okay. Okay, the next example, we have two different differential equations. As you can see, the difference between these two equations is this term. Here we have 2 times by x dot, and this term in vibration is called the damping terms. You will see later when we extract the governing equations for a system with damping, we have another extra term in our equation of motion, which includes the first derivative of the x with respect to time, and it's called the damping terms. Here you can see the initial conditions, because here this is a equation in terms of time. We have initial conditions, so here we call them initial condition, not boundary conditions. In the first equations and second, in both of them, the the initial conditions are the same. We have x at t is equal to 0 is equal to 1, and x dot at t is equal to 0 is 0, or the velocity at t is equal to 0 is 0. But in the equation, in the first case, we have 2 times by x dot, but in the second equation, there is no damping. And also both equations are homogeneous. As you can see, we don't have any non-homogeneous term. So in vibration, we call them free vibrations equation. So we need to solve these two equations, and also we need to plot the response and compare the solution and compare the results for these two equations. Here, the first equation, as you can see, we have homogeneous equations with these boundary conditions. So the total solution is equal to the homogeneous solution. I mean, we don't have any particular solution, and the particular solution is 0. So we need to form the characteristic equation. The characteristic equation for this equation is alpha squared plus 2 alpha plus 3. As you can see, the coefficient of x double dot is the coefficient of alpha squared. The coefficient of x dot is equal to the coefficient of alpha, and finally plus the coefficient of x. This is an algebraic equation from order 2. Easily you can solve it from delta method, and I will show you all of the formula. The required formula for the delta method is uploaded on Moodle. After this slide, I will show you how you can get this file and how you can have access to this file on Moodle. So this is the alpha 1 and alpha 2, the roots for this equation. As you can see, the roots are complex conjugate, and we have one real part. We have one real part and one imaginary part. So the xt, or the response, is equal to exponential minus t times by c1 times by cosine square root of t. Here you can see a square root of 2 is the imaginary part, and exponential minus t, which minus 1, is the real part. So this is the xt. The next step, we need to obtain the c1 and c2 by using the initial condition. As you can see, we don't have any particular solution, so directly from the homogeneous response we can jump into the initial conditions. Of course, here I write boundary condition, it should be initial condition. At t is equal to 0, x is equal to 1, it means here in this response we should substitute t is equal to 0, it's equal to exponential 0, cosine 0 and sine 0, so this term is 0, and it's equal to c1 times by 1 times by 1 must be equal to 1, so c1 is 1. And for the second coefficient, we need to obtain the derivative of x with respect to time. Here we have two functions, one exponential function multiplied by a cosine and sine function. So the derivative of this equation is the derivative of exponential part times by cosine plus sine, plus the derivative of cosine plus sine times by exponential parts. Okay, so you can calculate the derivative of x with respect to time, and then you can substitute t is equal to 0 and simplify this equation. Again, you can extract this equation, and we know that c1 is equal to 1 from previous equation, and we can extract that c2 is equal to 1 over square root of 2. So this is c1 and c2, and we can substitute into the main equation, into the main response. For the second one, as you can see, there is no damping terms. So again, we need to form the characteristic equation, which is alpha squared plus 3. Here we have two roots, plus minus I times by square root of 3. So xt is equal to this term. As you can see, there is no exponential term because there is no real part in your roots. So xt is equal to c1 cosine the imaginary part, which is a square root of 3, plus c2 sine square root of 3 times by t. This time we will have again the same initial conditions. X at t is equal to 0 is equal to 1. Here you substitute t is equal to 0, so we will have cosine 0, sine 0, which this time is 0. So c1, similar to the previous part, is equal to 1. But for this part 2, the second initial condition, we need to obtain x dot, which here x dot is equal to c1 times by minus square root of 3 times by sine square root of 3t, plus c2 times by square root of 3 times by cosine square root of 3t. If you substitute here t is equal to 0, we will have minus c1 sine 0 plus c2 cosine 0, and it must be equal to 0 from this initial condition. So here this term is 0. We will have c sub 2 times by square root of 3 is equal to 0. So we can conclude that c2 is equal to 0, and we can substitute here, and we can obtain xt for this part, which is equal to cosine square root of 3. If you plot the results for these two equations, you can see this one, of course, there is no color here. This one, let me show here. This graph, which is fluctuating, and the amplitude is remained the same. As you can see, the amplitude is the same. This graph is for the second part, but this graph, as you can see, that it doesn't fluctuate, or there is no vibrating in this one. And this is the solution for equation in part 1. And this is the effect of the damping terms, as you can see, because of the damping. After this initial condition, as you can see here, it starts from 1, because x at t is equal to 0 for both cases was equal to 1. So it starts from x is equal to 1, but before 4 seconds, you can see that the amplitude for the first equation is 0. Here at this time, before 6 seconds, you can see that there is no amplitude and the system is at rest, or its amplitude is equal to 0. But for the second case, as you can see, after 6 seconds, again, the amplitude is the same and there is no decrement in your amplitude because there is no damping in your equations. Okay, and we can discuss, of course, in vibrations, the effect of these parameters. Okay, any question from this example? No question? Okay. Okay, so let me show you how to find and how to calculate, solve the algebraic equations here. Let me first share my, here, this is my Moodle page. If you go through to MM366 Moodle page, in week 13, here, this is the solution of algebraic equations. Here you can see this is the solution of algebraic equations. The first part that you need is the quadratic equations, alpha x squared plus bx plus c, and it's equal to 0. The solution for this equation using the delta method, you can easily use this formula. We need to obtain delta, which is b squared minus 4ac. B is the coefficient of x, a is coefficient of x squared, and c is the constant part. So you can use this equation to obtain the roots of the equation. Of course, these are the 4 cubic equations that we don't need, at least in these chapters, we don't need them. And only you need to obtain the quadratic equations and delta method. Again, you can see we have 3 different cases for the roots of these equations. Okay, so you can use this equation and this file to solve the algebraic equations and obtain the roots of characteristic equations. Okay, if you don't have any question, we can wrap up these sessions and we continue on Wednesday. Okay, thank you for the attention and have a good day. Thank you. Bye.